Hey guys, my name is Srikkanth, and today I'll be going over the solution to FEWDIFF. Um, about me, well, I'm a recent 2020 graduate in electronics from NIT Trichy, and uh, my CodeChef ID is uh, this, and you can find me on CodeForces and other uh, coding platforms like AdCoder, in which my name is Srikkanth R. Yeah, so I've been doing computer programming for like a while now, and uh, yeah, today I'll be going over the solution of this question. The third most solved problem in Div 1 today. Um, very few people solved it, like 20 people solved it. So it's definitely not one of the harder problems. Even Gennady had some problems with it. He direct after the first two problems he went for this problem, although it was on zero for like the first half an hour or 40 minutes, and yeah, he had a lot of wrong submissions to this. Yeah, but I mean, he finished first at the end. Um, yeah, so let's go. Today I'll be covering the solution for this. I'll start out with the problem statement, and uh, I'll try to break down the solution for you, and we'll go over solutions for the subtasks which are easier in the beginning, and then yeah, we'll see how to get 100 points for this problem. Tomorrow at 11 p.m. Radoslav will do a tutorial on permutation split, and then on Monday we'll be having the session on the last problem. So feel free to tune in if you're free. So yeah, I'll be taking doubts as well in between. So you can use the live chat on YouTube to post any questions that you'll be having, and I'll get to those questions as and when you ask them. So yeah, about this problem, you're given an array. Uh, you're given an array of size n. Let's say a1, a2, and so on till an. And in one operation, you're allowed to take any value and change it to any other value you want. Okay, and we want to make the array good. So we want this array to satisfy some property. So before we see what the problem is, yeah, this is like a common uh, type of problems that you will come across in computer programming if you do it for a while. So the common theme is you're given some operations to perform and you want to optimize. We want to make the smallest number of operations in order to satisfy some property. Okay, so so here before we get to the property, we'll see that it is actually not quite simple. So the way to solve these kind of problems is first get an understanding of these properties, either by constructing examples, etc., which will help us in solving the problem. So yeah, so in this problem, a sequence of length k is good if it has at most k by 2 plus 1 distinct elements in it. So it has maximum k by 2 plus 1 distinct elements, which means probably for so there are half as many distinct elements as there are numbers in the array. and we want to transform this given array so that every subarray is good. Okay, and so this is the important property, that we want all contiguous subsequence or subarrays to be good. Okay, so for all subarrays of different sizes, we need them to be good. So let's consider subarrays of small sizes first and see how our array should look like. So let's consider k equal to 1 first. Okay. So for k equal to 1, you have k by 2 plus 1 is 1.5. So there are at most 1.5 distinct elements, or just one distinct element. Sorry. Yeah. So there's just one distinct element, which is true for any array. So we don't need to check for k equal to 1. This property of good is trivial. Okay. So similarly for k equal to 2, we have k by 2 plus 1 is 2. So every subarray of size 2, it can have maximum 2 distinct elements because there are only 2 elements in it. So for we don't have to check it for k equal to 1 and k equal to 2. Let's start with k equal to 3, where things get interesting. So an array of size 3 is good if it has max sorry, I got a bit lost there. Yeah, so if it has maximum k by 2 plus 1, which is 2 distinct elements. So here things get interesting. So we have 3 elements, and they can have only 2 distinct elements, which means that at least 2 of them among these 3 elements must be equal. So we could have, so let me call A to be the most frequent element and B to be the next frequent element. So we can have stuff like AB, ABA, and BAA. So these are the 3 situations that we'll be having. So so if we want to make our array good, that means every subarray of size 3 should have maximum 2 distinct elements, which is equivalent to saying that at least 2 of them are equal. So any set of 3 consecutive elements you take in the array, 2 of them must be equal. So that's for k equal to 3. We'll not go over k equal to 4 specifically, but so we want to make every subsequence good, right? So if every subsequence is good, subsequences of size 3 are must also be good. So if we consider let's say we have made all subsequences of all contiguous subarrays of size 3 to be good. Okay, so let's consider subarrays of size 4. So we have these 3 elements. Remember, among these 3 elements, at least 2 of them must be equal. So if we consider this 4th element, we know that both this subarray as well as this subarray should satisfy our property. Okay, so there are 2 elements equal among the first 3 elements, and there are 2 elements equal amongst the last 3 elements. Okay, so if this element right here, let's call this x, if x was not equal to both of these elements, let's call them y and z. So if x is not equal to y and x is not equal to z, okay, so that means that consider these 3 elements, right? So if x is not equal to z and x is not equal to y, that means y must be equal to z. Okay, because here what I'm doing is I want to make all contiguous subsequences of the resultant sequence to be good. Suppose I have made all subsequences of size 3 good. Okay, so I have to make all subsequences good. So first, let's assume that I have made all subsequences of size 3 good, which I anyway have to make in the end. Then what we have here is that in the first 3 elements, 2 elements must be equal, and in the last 3 elements, 2 elements must be equal. And if this fourth element that I have, so we need to consider the subarray of size 4, and we need to make it good. So remember that YZX should be a good sequence. So if X is not equal to Z and X is not equal to Y, this must imply that Y equal to Z. Only then these 3 elements can form a good sequence. So good sequence, yeah. So what does this mean? So this means that so let's find the number of distinct elements that we can have. Sorry. Number of distinct elements that we can have in this sequence of in subarray of size 4. Okay, so we have this if either x equal to y or x equal to z, then the number of distinct elements does not increase after the first 3 elements. So after I've inserted x to this first 3 elements, I get a subarray of size 4, and I want to calculate the number of distinct elements in this subarray. If either x equal to y or x equal to z, then the number of distinct elements will not increase when I inserted this new element x. So in that case, the number of distinct elements will be 2. Okay, in the first 2 cases, if either x equal to y or x equal to z or y equal to z. So in the first case, the number of distinct elements is 2, and similarly in the second case also. In the third case, the number of distinct elements that we can have is y equal to z. So these 2 elements can be distinct. So the number of distinct elements that we can have in the third case is 3. Okay, so remember that we already made all subsequences of size 3 to be good, and once we have done that, we see that the number of distinct elements, maximum number of distinct elements in all 3 cases is 3. So so for k equal to 4, k by 2 plus 1 is 3. So if we have already satisfied the property of every contiguous subsequence of size 3 to be good, then every contiguous subsequence of size 4 is also good. So this is an interesting thing. So if we have done it for 3, then we have done it for 4 as well. So what about 5? Right? So a similar situation happens with 5. So let's assume that this subarray of size 3 is already being made good. So at least 2 of them in these 3 are equal. Then when we add 2 elements, so again we delve into these cases, right? So let's consider everything diligently. So right, so if we have either these 2 cases, x not being equal to z and x not being equal to z or y, then remember that this is an additional subarray that has to have 2 elements equal. So if x is not equal to z, then this element must either be equal to z or either be equal to x. So in that case, the number of distinct elements didn't really increase after the first 4 elements. because the fifth element was either equal to the fourth or the third. So yeah, similarly, you can verify that uh, all subsequences of length 5 are also satisfied if all subsequences of length 3 are good. Okay. So what I want to focus here is that whether you add one element or you added two elements, uh, the sequence of size 5, it was still good, right? So you can extend this idea, and you can get that for all values of k greater than 3, uh, you have maximum k by 2 plus 1 distinct elements, right? So another way to think about this is assume that you have only uh, assume that you want to satisfy this for only subsequences of size 3. Then how should your array look like? So as I said, if you take any three consecutive elements, at least two of them will be equal. Okay, so you could have something like a b, and then followed by a b, etc. So notice that the number of distinct elements was 2 here, up to here. So if you want to add a third distinct element, that means that the previous two should have been equal. So you cannot have ABC, right? Because this means, so when I say ABC, I mean that all three are distinct. So if you have like a subarray like ABC, then that doesn't satisfy our property. So this cannot happen. So whenever a third distinct element comes, the previous two elements must be equal. Okay, so a way to think about it is you can have at most one element not being paired with someone else. That is the last element, and everyone else must occur in pairs. So the maximum number so if you have something of length k, the maximum number of distinct elements that you can have is k by 2 plus 1. If you follow this constraint that among every three consecutive pairs, at least two of them should be equal. So this was kind of uh, an easy observation that was to be made for this problem. So every subarray of size 3 of size 3 should have two elements equal. So this is equivalent to making the array good. That is, uh, this is equivalent to making every contiguous subsequence of the array good. So instead of focusing on this, we have simplified this property, and we have yeah. So this is an easier property to check. Okay, so if you wanted to check uh, if all the contiguous subsequences of the array is good, you don't have to explicitly consider every subsequence, every contiguous subarray. Rather, you can just check every subarray of size 3 and check if it has two elements equal in it or not. And yeah, so with this simple property, we can it'll be easy to solve the problem if we consider the problem to be this one. It's the equivalent problem instead of the original one. Uh, so at this point, I mean, this is a very crucial point in the problem. Like everything else follows from this. So if you didn't understand anything here, uh, I would ask you to ask a question in the chat so that I can clear it up for you. Okay, so I'll just go ahead then. Right. So yeah, once you make this observation, right? Uh, yeah. So uh, let's consider the sample. Right? Say, let's consider this one. It's already so. Let's consider this one. It's a good example. 1, 2, 3, 2, 1. Okay. So this is clearly not a good array because, for example, this guy has 3 distinct elements. And then again, this array has 3 distinct elements. So so one way to make this good would be to change 3 to 2. Yeah, this is good because for every subarray of size 3, you have max 2 distinct elements. So yeah. So now the question is, which values do I change, and to what value do I change them, right? So let's consider the last element. Okay. So let's consider an, the initial value of an. So so the only subarray that I'm worried about is this one, containing an is this one. So this is the only subarray of size 3 containing an, and I would like there to be only 2 distinct elements here. So what value do I change an to? Okay, so I could change an. So if suppose all of them were distinct, so I could change any of these. But my question is, what? So what I'm wondering is, what should the final value of an be? Should it be an, or should it be something else? So if it is something else, what possible values would I want to change an to? So I could change an to an minus 1. I could also change it to an minus 2. That would also make the subarray good. But you have to remember that we can make this operation on an minus 1 and an minus 2 before we make them on an. So if I want an to be equal to an minus 1, I cannot say what the value of an minus 1 would be in my final configuration, or at least I don't know it now, right? But what I do know is that the value of an, if I change it to, it's going to be one of the values in the array. Okay, so if I have an array of like 1, 2, 3, 2, 1, there's no point in changing this 1 to a value other than 2 or 3. Okay, because my end goal is to make elements equal to each other. So yeah, so the final value of an can take only can take only n possibilities. We will see later how to reduce this, but for now it's obvious to us that an can have only n possibilities, right? An, the final value of an. So let's say that after I do all the operations, my array is bn, uh, b1, b2, and so on till bn. So let's assume that a1 and so on till an is the first array, and b1 and so on till pn is the second array. Is the array after I perform all the changes, all the operations. And remember that the operation that I'm allowed to make is I can choose any element of the sequence and I can replace it by any integer I want. Okay, and there is no point in choosing an integer twice, choosing an element twice. Like if I'm going to choose this guy, there's no point in choosing him twice. So there are only n possibilities for the last guy. I only choose him once, and in that one time, I'm going to change him to one of the values in the array that's already there. So there are only n possibilities for this guy, and for every element in the array. Okay, so there are only going to be n possibilities. So let's say that I'm going to change an to ax. Okay. So the cost for this operation is n not equal to x. So if n is equal to x, then I don't have to perform any operation and get the same. But if n is not equal to x, then in one operation, I can change an to ax. Okay. Right. So let's consider the, let's fix the value of bn to ax. So let's let bn be equal to ax. Suppose I changed the value of the last element to ax. Then what happens is I have this array bn minus 1. And notice that bn minus 1 is also good, right? So since b1 to bn was a good subarray, this is also a good subarray. And if bn was fixed to ax, so then either bn minus 1 is equal to ax, or bn minus 2 equals ax. So I'm considering the last three elements here. So two of these three must be equal. So either bn minus 1 equals ax, or bn minus 2 equal to ax, or bn minus 1 equals bn minus 2. Right. So in this case, if bn minus 1 equal to bn minus 2, then I don't really care what the value of the last element is. So that is fine. But if bn minus 2 equal to x, this is one possibility and this is another possibility. So what I need is amongst all possible ways of making the first n minus 1 element. So note that all the operations are independent of each other, right? So I can make an operation on the first n minus 1 elements independent of the operation of the nth element. So if I consider the first n minus 1 elements, right? So the sequence of operations that I did is a valid solution for the first n minus 1 elements, right? So this is the same problem that I'm solving, but on a smaller size array, right? So I considered the array of size n, and I wanted to make it good, right? The and let's say that the last element, and I know that the every element in the final array must be one of the elements in the first array. And I'm assuming that the last element, I've changed the last element to ax, like one of the uh, elements from a1 to an. So x could be equal to n, in which case, yeah, I have no cost. But if x is not equal to n, then I have to pay one operation to get it changed to ax. And I know that this is going to be a valid solution for the first n. If you just consider the first n minus 1 elements and you consider the same problem, this is going to be a valid solution there. And in order to determine what this ax should be, either should I make ax to be equal to bn minus 1, or should I make ax to be equal to bn minus 2, or whether I don't care what ax is, I need to know the values of bn minus 1 and bn minus 2. Okay? But we already know that for every bi, it has only n possibilities, right? So let's calculate this, right? So I need say answer let me consider this answer of prefix of the array. So here, let me just use a normal answer of say first I elements. Uh, what is bn minus 1 and bn minus 2? What are the last two elements of the array? Let's say there are x and y. Okay, so let's say answer of 1 is to I comma x comma y is the minimum number of operations to convert a1, a2, and so on till ai to b1, b2, and so on till bi minus 1, bi, bi, with bi equal to y and bi minus 1 equal to x, right? So the reason that I'm fixing both of these values, bi minus 1 and x, bi, is so that I can get uh, what the last element should be. Okay, so yeah, so if so I can have n possible values, x can have n possible values, y can also have n possible. So this is a function with three variables, each having n possibilities. So there are n cube different quantities that we want to calculate. And how do I go about calculating them, right? So uh, if I have a prefix of size I, and let's say I want this one to be equal to y, this one to be equal to x, then answer of I comma x comma y is okay. So first I have to make the ai to be equal to ay, okay? And then I have to make ai minus 1 to be ax. Okay? So this should be is ai equal to ay AI is not equal to AY, then I have to pay one operation to convert this. Then AI not equal to AX. AI not equal to AX, okay, plus, right, yeah. So I made AI to be equal to AY, but I have to still convert these guys. So AI minus 1's value I know is AX. But what about AI minus 2? So AI minus 2 could again have anything from A1 to AN, right? So yeah, this is taken care of by a recursive function plus sort of I minus 1, comma. So I know that the last value here must be X, but the previous one I don't know. So that could be any of the n possibilities. And right. So, and I have to take min of all of them. So minimum among all possible values for k. So let me just zoom out a bit. So just write it again. So if you consider the first I elements and say that the uh, last element is y, the previous element is x, then first I have to is minimum over yeah over the last element x plus 1 k can be anything from that. Okay. So we have nq variables to calculate because I can be anything from 1 to n, x can be from 1 to n, y can be 1 to n, etc. And yeah, this is just the first case, so I have to take care of this case also. So that would be uh, this is one case, and then the other case would be answer I minus 1 a comma k. Minimum of these two quantities is what I have to calculate, and I had so k has n different possibilities. So just calculating this recursion would give you a complexity of about n power 4 because you have n cube variables to calculate, and for each time you spend O of n time in calculating this min argument. So I should probably put that in here. This one and these two. So this is not going to pass even the first subtask, right? Because Yeah, we have 200. Maybe you can squeeze it in. But you can recalculate the minimum overall k for this and the minimum overall k for this, and you can reduce this to O of n cube, which will successfully pass the first subtask. And this, I think, should be fairly easy if you're able to figure out this property that every subarray of size 3 should have two elements equal. Then it's just a matter of figuring out, yeah, I have only n possible values that I want to change to, and what do I change the last element to if I change it at all. And then you can see that the last element is part of only one subarray of size 3, and that falls into these three cases, right? Either the last element is equal to the previous, or the one before that, or the last two elements are equal themselves. In this case, you don't do any operation at all. You don't care what AX is. So that gives you this, yeah, this fairly obvious recursive dynamic programming solution, which will get you 20 points. A lot of people had 20 points in this one. Possibly they had this something similar to this. Yeah, a lot of people had 20 points. Okay, so to optimize this, okay, so the only uh, thing that we're going to make is, so we had n possible values for every element, right? And if you think about it, like here, when uh, yeah, when I wanted to get, when I wanted to make this array good, I wanted to make, let's say, the last element equal to one of these two. Uh, yeah, you would think that you would need to fix an to be equal to either an minus 1 or an minus 2, right? But uh, uh, so the intuition is that the value that I'm going to change to should be close, uh, should be nearby in the array. So if I want to change an to some other value, that value should be close by. So what do I mean by that? So let's uh, instead of trying to change this element to one particular value, let's try to find out which pair of indices are equal to each other. Okay, so if I construct this array, let's ask the question, in my final array, which pair of elements are equal. For every three elements, at least one pair will be there. Three consecutive. Okay. So how should the graph look like? So if as let's assume hypothetically that I draw an edge between the two elements that are equal. Okay. So in this case, let's say these two elements are equal. So I draw an edge like so, saying that I want these two elements to be equal. So I not necessarily fixing what the value of this guy should be, or what the value of this guy should be, or whether I'm going to change this one to be equal to this one, or whether I'm going to change this one to be equal to this one, or whether I change both of them to be some common value. Okay, so I mean, obviously I wouldn't do that, uh, but yeah, those are all possibilities that I'm open to. Okay, so I'm just worried about which pair of elements are going to be equal after I made all the operations. And if you think about this, uh, you can make a nice observation that let's say you had, so every three consecutive elements should have an edge, right? So uh, if I have something like this, then one valid solution would be this sort of pattern. Okay, so if you consider every three consecutive, there's an edge involving those three elements. So here I say that I want these two elements to be equal to each other. So I draw this edge. So this subarray of size 3 has only two distinct elements. And similarly, this subarray of size 3 has only two distinct elements. What about this subarray of size 3? Yeah. So I haven't made any of them to be equal via these edges. So this is, so I need to add an edge here. So let's say I do this. So the idea of considering, so similarly, what about these three? Again, doesn't have an edge amongst them. So one possible way is to add this. Okay. Yeah, so now, okay, so if you consider this new thing that I've drawn here, so when I draw this arc between two nodes, I'm saying that in my final array, those two values are equal. Okay. So in this diagram, this arc is unnecessary because without that itself, you have every three consecutive elements covered. Uh, and similarly, this one is not required. Uh, so either I can remove this one or I can remove this one. I can't remove both of them. Right? So uh, yeah, so I'm going to think about how to draw these pairs. And once I draw these pairs, I have to choose which operations to do to make these pairs actually equal, which will come later. But an interesting observation that you can make while trying to uh, make these pairs equal is that you never have to do these kind of jumps where you're setting an element equal to someone further away from you. Okay, so let's see why. So if I make these two elements equal to each other, then this this subarray is covered. That is, this subarray has maximum two distinct elements. So for this subarray, I have satisfied the property, and then for this subarray also I have satisfied the property. So inadvertently, by making adjacent elements equal to each other, I'm able to cover more subarrays. Okay. Yeah. So this tells you that there is no need to make uh, elements who are more than one unit away from each other, which are not adjacent, equal to each other. Okay, this provides kind of an intuition. But you can formally prove this by constructing like a few cases. Suppose you had, suppose you made these two elements equal in some configuration. Okay. Uh, I claim that by removing this and making these two equal instead, definitely does not hurt. Like, you can make this change and still uh, not be affected in terms of the number of operations you do. And why is that? That's because uh, if you consider the neighboring subarrays, right? These three elements and these three elements, they have to be covered by some edge. So amongst these three elements, two of them should be equal to each other, and amongst these three, two of them should be equal to each other. And if you consider uh, so let's say these two were equal, and uh, these two are equal, right? So you can remove these edges and rearrange them like so. So you had one, two, three, uh, three arcs here. You can have the same three arcs here and still cover the same, fully cover the same element. So if you check here, every three elements have at least one edge amongst them. So what this tells you is that in our relation amongst uh, pairs of elements that we want to make equal, we never have uh, we never want to make elements that are not adjacent to each other equal to each other, or there exists an optimal solution where uh, I only want my only sole purpose is to make adjacent elements equal to each other. Okay, so what does this mean? This means that uh, okay, so now you can reduce the if you think about these equivalence relations that I've drawn via these edges here, uh, a single element can have maximum degree 2, right? Either it can have this arc or it can have this arc. Okay, and you never have to have three arcs adjacent to each other. So if you have this situation, you can remove this arc and you can still have a valid solution. So you never have three arcs adjacent to each other. So maximum what you have is either one arc silently like this, or two arcs continuous to each other like this, and neighboring arcs separate. Okay, so these are the only arcs that you have. So that means that one way to do to make these two elements equal and these two elements equal is to copy to change this guy to be equal to this value, and to change this guy to be equal to this value. So in either case, whether a node is part of these two consecutive arcs or whether a solo arc, uh, AI can have only three possibilities. So AI can have either AI minus one or AI plus one or AI itself, where I don't perform any changes to it. Okay. So one thing that I'd like to note here is that these arcs that I've made here are arcs representing an operation that I'm making. Okay. So when I draw an arc here, I say that I'm saying that I'm making these two elements equal via some operation. Okay. So it could happen that uh, these two elements are equal and they are already equal in the given array. So in that case, you could imagine that I have a arc here saying that these two elements are equal. In this scenario, I don't have to have an explicit equivalence relation from my side covering this. So whatever operations I am going to make, I'm only going to make adjacent elements equal to each other, and that gives you this property that a given element can have maximum, it can have only three, or if I consider that I'm going to change it to only these three values, I will still be able to obtain one of the optimal solutions to this problem. Okay, so instead of considering n different values like I did here, uh, yeah, x could be anything from 1 to n and y could be anything from 1 to n. Instead of having n different values, this greedy property that I had derived, rather maybe uh, unclearly, sorry about that, but if what this says is that AI can have only these three different values. Instead of having n different values for this, I consider only three different values for this. Either this element is equal to itself, or the previous value, or the next value. And this reduces the number of states in your dynamic programming by n squared. So earlier it was n by n, n by n by n. Now it's only n by 3 by 3. Okay, and yeah, this reduces your complexity from n cube to O of n. And yeah, a lot of contestants, they kind of expected this, but what they did was the size of the window they had was larger than 1. So most of them had a window of size 3. So they assumed that AI can have values either AI minus 1, AI minus 2, or AI plus 1, or AI plus 2. So they had uh, a DP like this. Uh, so they had more states in their DP. So they had uh, 1, 2, 3, 4, 5. Yeah, they had 5 different values. Some of them even had uh, uh, 7 different values, I believe. They had the window size 5. Some of them even had 11 different values. So this would increase the time complexity of their solution, and the time limit is actually very strict here. Time limit is only 1 second. So some of these solutions didn't pass because yeah, the solution complexity was n into this window size square, 3 square. So the one that I described here is n into 3 square, which comfortably fits. But yeah, some of them wrote 5 square or 7 square that didn't quite fit into the time limit of 1 second. Uh, so I hope you understood a bit of why I only wanted adjacent elements to be equal to each other. I try to provide some intuition behind it. Yeah, so instead of in the first place asking what value should I change it to, it helps to think about what pair of indices should be equal to each other in the end. So if you think in those terms, uh, it kind of becomes obvious to you that I will never want to make uh, indices that are at distance more than one away, indices that are not adjacent to each other, equal to each other. So I could convert a situation like if I wanted to make these two guys equal, instead uh, I could have this thing going on. So because this covers more subarrays than this, so this would satisfy only this subarray, or this would cover only this subarray, but this would cover two subarrays, mainly this guy and this guy. And if you work out the cases a little bit, you can prove that uh, firstly, you never have equivalence relations like this in your final subarray, and you never have uh, equivalence relations like this three continuous adjacent equal to like this. You never want to have edges like this. And so finally what you have is you have edges only, equivalence relations only of this form, and that tells you that uh, the only possible values that I can have for an index, or I could construct an optimal solution only considering the neighboring two values, either the left or the right. I don't have to consider anyone else. I don't have to make this number equal to anyone else in order to get uh, an optimal solution. Okay. So uh, yeah, that's about it for the overflow solution for this problem. Uh, I'll try coding this up in a second. But before that, I'd also like to say about this. Yeah. So we had actually, I had come up with an n square solution also for this in the beginning. It took me quite a while to figure out the overflow solution to this. Uh, but the n square solution is basically based on one of the previous observations that I just glossed over, that uh, for some starting from the beginning element. So if you work out a few examples and try to find all possible, try to construct some sequences that satisfy this property, you will come up with the conclusion that uh, for some prefix of the array, there will only be two distinct elements. And once you start off, so if suppose there was a third distinct element in your subarray, let's call it C, the two elements before that would be equal to each other, like so. Okay. And then yeah, you would move on. So this guy's value would be either A, and then you could have CA, and so on. And then if you want to have a fourth distinct element in your array, say D, the previous two elements should be equal to each other. So you should have A, D, like that. So you can split the entire array into uh, kind of these subarrays that have only uh, two distinct elements in them in total. So this gives you a simple TP solution. If you consider suffixes separately, so if you say TP of x is the answer for the suffix x plus 1, sorry, ax plus 1, so on till an, you can construct TP of x from TP of y values. So what you say is that for some for some prefix, I have only two distinct elements, and after which I have another good subarray. I have a good subarray followed, and I have this prefix such that the last two elements are equal, And in total, this has maximum two distinct elements in this prefix. So this would be, to sum this up quickly, if p of x is minimum dy, y greater than x, plus cost to make 1 through x through y minus 1 have maximum two distinct elements, and last two elements equal. Uh, yeah, so this is like a suboptimal solution for just to cover the subtask. But most people who got uh, 50 points here was because of the time limit being too strict, and yeah, they had to just to make constant optimization to get over this. Yeah. And those that had 20 points probably had an O of n cube solution like the one I described earlier. So, any questions till now? Okay, so I'll just quickly close this up, and uh, you can ask any questions that you might have had, especially this part, proving that uh, every element can have that there exists an optimal solution where you only have to make the current element value equal to the previous or the next one. That's basic. That's the observation that could get you 100 points. So, uh, with so the same definition here, but okay. So here, whenever you create like or 2D or 3D array, it's probably best for performance in caches if you put the elements with put the smaller sizes first. Like, I mean, it doesn't matter much, but might give you like more performance. Right. Right. So there are only two elements. There's nothing to check. Otherwise, yeah. So, uh, so there are three states, right? So one is uh, before either AI or AI remains. These are three states here, and here I want to find out the changes I made for the current element and the previous element, the one before that, similar to the definitions here. So the only difference from the group to the optimized one is the change in the number of candidates for X. Uh, so let's see. So this is either whether my uh, amount of equal to the previous value or the current value or the next value. So let's initialize it for the base case, which is if I'm going to make something equal, I mean, I'm going to change any of them. Either I, so I is for the previous element, changes any change I made to the previous element, and J is for the uh, any changes I made to the current one. So if they're not zero, then I have to pay one for each of them. So this should be here. And yeah, they don't have negative indices. Clarify that. So minus 1, 0, 1 are the three states for the current for the last element and in the previous one to calculate the same kind of recursion that had listed over here. So yeah, so that's left is for the values. So let's say I is for changes made to the current one, A for the previous, is the one before that. So uh, element should be of yes, minus okay. This is a valid then good. We just realize everything to so for initialization, yeah, I'm just gonna say to infinity or some large value so that through the means I will eventually obtain the correct value. See, good. Let me just check. Seems good. That's a good. Uh, should be good. We're here. See. Okay, that's weird. Nice. Okay. Finally, just get to this was the cells of launch. Okay. Did I already? Oh yeah. Okay, so if you guys have any questions, you can feel free to ask in the chat. Um, Cool. Then I think we can move that, right? Yeah, thanks for tuning in. And tomorrow, Radoslav will discuss the solution for the permutation problem. Yeah, that's an interesting problem. Turns out it's a knapsack problem. Turns out, yeah. So for full details, you can see tomorrow. Radoslav will be explain the solution. Uh, that's it from me. Um, yeah, there's a feedback as well shared, I believe. So please fill that. So this is my first sentence. So if uh, yeah, I was not clear in many aspects, it's because yeah, this is my first time doing it. So please give the feedback so that help me improve next time as well if I'm doing it again. Uh, and that's it. Great. Good night. Thanks for tuning in.